How you doing? I'm Mr. Rose, and today we're going to continue to talk about our DC circuits. Now, before we jump into charging an RC circuit, which is a resistor-capacitor circuit, I want to talk briefly about just a multi-loop circuit and summing all of our resistors. We kind of skipped this in our last lecture. So here I have a multi-loop circuit, otherwise known as a parallel circuit, with resistor 1, resistor 2, resistor 3. I've applied the junction rule if I had the loops going through, so I have a total current from the battery, I1 going down my first branch, I2 and 3, so I2 plus I3 has to equal my total. I1, here I have I2 going down my second branch, which only leaves me I3, and I have I3 going down my third branch. As we traverse around, we can see after this junction I have I2 plus I3. When it meets I1, I have I total is I1 plus I2 plus I3. Very simple math. Now, we want, just like we did with a series circuit, we can do the same thing for a parallel circuit where I combine everything to have an equivalent resistance. Now, a parallel circuit is when we have resistors wired together from each side. In other words, I have potential at A and B, my potential A and B wired across that resistor, and that resistor. So our rules are a little bit different. We should be able to see that the voltage on each branch, that branch, that branch, that branch, is the same because of the way it's wired. Again, our potential here is wired essentially directly to either end of our resistors or our circuit element. So to find the currents in each branch, I can say the current I1 is just my potential divided by resistor 1. The current in I2, potential divided by R2. Current in I3, or current I3 is the potential divided by the resistance of 3. So if I sum all that together, my total current, we can see, I1 plus I2 plus I3, that's just an application of the junction rule, is equal to my total potential times, this is V equals IR, so my total potential times my total resistance here, 1 over R1 plus 1 over R2 plus 1 over R3. So what we're looking at is this equivalent resistor, IEQ, this should be REQ, my equivalent resistance is really this function right there, 1 over all of that. So we can see 1 over R1 plus 1 over R2 plus 1 over R3. That is my equivalent resistance. That's equal to 1 over what we're calling REQ. So my final equation, my total current, is my total voltage divided by my total resistance, REQ. So we can say that 1 over the equivalent resistance is equal to the sum, as I goes from 1 to n, of 1 over Ri. If it's easier for you to picture, I could say that resistor 1 times resistor 2 divided by resistor 1 plus resistor 2. Obviously, that can expand out to more and more resistors. So this is just simple summing up a multi-loop or a parallel circuit. Now we're going to get to the bulk of today's talk, which is charging an RC circuit. Now, an RC circuit, again, is a circuit that has a resistor and a capacitor. Now, at some time equals 0, I have my battery here. I'm going to close this switch. When I close that switch, the capacitor, which is a device that builds charge up, is going to start to get charged up. At time equals 0, basically there's no charge here. All of my potential would have to be across that resistor. And this capacitor essentially would act like a wire at that instant the switch is thrown. Now, as charge goes, I can add my EMF, and I know my current would go in that direction after my switch is closed. So I'm going to start to get a positive charge up on that plate, a negative charge on the bottom plate, and we're going to start to build charge. So at t equals 0, the moment my switch is closed, I start to charge my capacitor. I get positive Q there and negative Q there, and we can recall the potential on a capacitor is Q divided by C. Now I apply my loop law, Kirchhoff loop law, nothing has changed. I have E minus I times R minus the potential. Now I'm saying it's minus, it's a negative here because the top plate is positive, the bottom plate is negative, so it's flowing in the direction that I'd expect. It's flowing from a high potential to a low potential. So E minus I times R minus VC equals 0, getting all the way back. That's an application of my loop law. Now I know that the voltage or the potential across the capacitor is Q divided by C, so I have E minus I times R minus Q over C equals 0, which I've labeled equation 1. Now it seems like a simple equation, but I have two variables. I have I and I have Q. But I do know that I and Q are related to each other by the definition of current. I is equal to dQ dt. So I can sub that into equation 1. I now have E minus dQ over dt times R minus Q over C is equal to 0. Now this is essentially my equation for charging a capacitor. Now it's not the easiest equation, it's a differential equation, and this is describing the variation of charge on the capacitor as time goes on. So we need to solve this diff EQ, excuse me, we need to solve this diff EQ, and we need to figure it out by, well, one, we need to satisfy my result mathematically, and second, it needs to satisfy my initial conditions. Basically, it needs to say at time t equals 0, Q on the capacitor is also equal to 0. In other words, the capacitor was uncharged. So we're seeing a time dependence on that capacitor. As t goes up, Q goes up until it's fully charged. Once it's fully charged, in our next lecture, we're going to learn about discharging a capacitor. So let's get right to the math. First thing I'm going to do, collect all of my terms, right? So I'm collecting terms over here. I have my voltage. I have my voltage, Q over C equals dQ dt times R. Well, now that I've collected my terms, I'm going to separate them back out. Seems kind of weird, but I'm separating them back out because I need to eventually integrate or differentiate. You can look ahead to see that it's actually integration. So I'm going to collect all my Q's on one side. So I'm going to bring the other things to the other side. So I have dt divided by R is equal to dq over E minus Q over C. Now I'm going to integrate, but integration looks hard. So I'm going to integrate dt over R from 0 to t, dq over my battery E minus Q over C from 0 to Q. Integrating this left side is easy. The integral of dt over R is a constant. My integration from 0 to t is just t over R. Equals the integral of everything over here. Now this is a messy integral. So for this messy integral, we're going to use U substitution. Quick refresher on what U substitution is. Basically, I'm going to pick my complicated E minus Q over C, and I'm going to set that equal to U. So U is equal to this bottom part. So now I would have the integral of dq over U. Well, I can't take an integral of a dq into U. So once I sub that in, dq over U, I need to take the derivative of U. So in other words, I basically want only U's over in my integral. So I have dq over U. I'm going to take the derivative of U, du dq, and the derivative of that, my derivative of U, is just negative 1 over C. Separate my terms because I need to sub in for that dq, so I have dq equal to negative C du. Now if I come over here, it's just the direct substitution. Basically, we're making our integration a lot easier. So I'm going to integrate. I have my left side, negative C du over U from 0 to Q. Well, C is a constant. Integral of du over U, we know is just the natural log of U. So nothing changes over here. Negative C times the natural log of U from 0 to Q. So when I sub everything back in, I sub in for my U. U is just E minus Q over C. Sub that in. The natural log of E minus Q over C. That's for my Q minus from 0. 0 over C is 0, just the natural log of E. I do two things here in one step. I'm going to bring this C over here. So now I have negative T over RC. Look, it's an RC circuit. Is equal to, clean that up, the natural log of E minus Q over E divided by E. I want to get rid of my natural log, so I'm going to clear my natural log by raising both to an exponent, bringing both to the E rather. So E to the negative T over RC equals to, everything else here stayed the same, E minus Q over C minus E. I can clear this up a little bit, bring over my epsilon. I say E to the negative T over RC equals my potential E minus Q over C. Collect all of my terms and simplify. Basically, I have the charge on the capacitor Q equal to CE minus CE times E to the negative T over RC. If I want, I could factor this out, and this should look familiar to you. A C times an E, the capacitance times my potential V. Let's look all the way over here. Capacitance, potential Q, maybe that looks a little familiar. So this gives us a charge, 1 minus E to the negative T over RC. So this is the charge, time-dependent charge on my capacitor. If I wanted to throw that into a graph, graphing Q versus T, where this is my charge of a capacitor, I could see that it is a nice exponential curve approaching a fully charged. Now, we keep saying fully charged capacitor. We should know that capacitors are never actually fully charged. That would take an infinite amount of time. But we get them really, really close. So now, if I want to take this one step further, perhaps, I know, again, I is equal to dq over dt. In other words, as I can see this, as time changes, I'm just very small amount dq, there are small changes in my charge. So, I'm sorry, dt, there are small changes in my charge. So I know dq over dt, which is equal to I, I'm now going to integrate my q over here. So the integral of this constant is just 0. I said integrate, I apologize. I'm taking the derivative, dq over dt. The integral of CE is a constant 0, minus the integral of CE, e to the negative t to the RC. This is actually like my final charge. So when I take the derivative of that, I have my current I is Q, and this is really my final charge, QF divided by R times C, and then the rest, the derivative of e to the x is e to the x, so e to the negative t over RC. We should start to feel okay about this because Q divided by C, well, that's just the potential difference. The potential difference divided by resistance is in fact my current. This solves my initial conditions, my math works out, and if I look at what we started with, let's come all the way back over here. If I say at time t equals 0, e to the 0 is 1, 1 minus 1 is 0, so I have q equals to just c times e. Oh, I'm sorry, 1 minus 1 is 0, that times that is 0, so at time t equals 0, charge is 0, which is perfect. At an infinite time, e raised to some infinite power, that's going to be 0. 1 minus 0 is 1, and then I have q equals CE, the charge on my capacitor. So this seems to work out. My math works out, I solve my initial conditions, and I know that as time goes on, I should have a fully charged capacitor. I hope this helped. Thanks for watching. I'll see you for one more lecture now that you're all charged up to see how to discharge a capacitor. It is a little bit easier. See you next time. Whoop, still going. Still going. Nothing outlasts the Energizer battery.